Thank you very much, Pamela, for this warm introduction. What I will talk about is deep learning. How many people here have heard of deep learning? Okay, that's the most. And how many people know what it means? I don't either, so it's fine. Okay, so the perspective that I will convey here is, I believe, probably a little bit different from what you're used to seeing. It's going to be more formal and more technical, down to earth. I'll define what it means, deep learning, what do we know, what don't we know, and what are the efforts that are going on right now. One thing to note is that this will be a perspective. Okay, so that's my personal view. By no means is this going to represent the universal truth. And despite being an Israeli, I'll try to be careful and kind of held back, mostly because we're being filmed. All right, so without further ado, let's begin. So bio, I guess I could skip this. Pamela told you much more. So if you want to kind of formally define what deep learning means, you have to start with statistical machine learning, because at the end of the day, deep learning is a special case. Right? So let's start with what statistical machine learning is not. Okay? It's not the approach of expert systems. Okay? Expert systems, that is the traditional approach for solving problems. Okay? Most of the problems, that are solved by technology are solved through this approach. Okay? I want to solve some problem. I know something about what I'm trying to do, and I design a solution explicitly. Okay? So for example, I know how hardware and software behave, and I go ahead and design this amazing piece of equipment, a laptop, and there you go, I have a solution. The main advantages of this approach are that, by definition, it's something that's understandable. It works well in many, many cases. Okay? A lot of things around us, the internet, laptops, cars, these are all expert systems that experts design. And also, you don't need a lot of trial and error. Once you know your materials, okay, if there's a car manufacturing company, they don't need to do a lot of trial and error with the car and have it hit a wall 1,000,000 times in order for them to design a car. Right? Nonetheless, there are some disadvantages to this approach, and that is that some problems are just too complicated for us to solve this way. And there are some problems that we tried for decades to solve by explicitly designing solutions, and it failed. Okay? Other problems are maybe, if you put a lot of effort into them, they're somehow solvable, but they require so much effort that it's just not practical. Right? And I'll give here an example. Okay? So suppose we want to write a computer program that detects pedestrians crossing a crosswalk. Okay? So this seems doable. Right? I have to define a set of rules that the computer will go through to locate people. Okay, so maybe I would search for these colored bars in this kind of type of angle. These would be the legs, and then I'd search for some area that could be the face, and somehow locate people that are walking through the crosswalk and have these bounding boxes around them. So when you look at this example, this seems like you would be able to come up with a set of rules that will give you the locations of people in the picture. However, when you try and implement this in general and have a general system that detects people, pedestrians, crossing crosswalks, then you notice that there are so many exceptions that actually the exceptions are the norm. The variability is immense. Okay, you could have different lighting conditions, different types of characters. They could be cartoons, or maybe these Teletubbies, people going with segways. They could be walking, your angle could be such that they're walking towards you. And really, there are a lot of possibilities. And people have tried for decades to define rule sets that would yield the locations of pedestrians, and it didn't really work. Right? What did work is a radically different approach. We might take it for granted these days, but in my opinion at least, it's something that's quite radical. And the idea is to, instead of designing a solution specifically to your problem, you define a big family of solutions, and you collect examples, and you learn from that. Okay, that's called statistical machine learning, and now let's be a little bit more specific. Okay, so instead of having one single algorithm, one single rule set to find pedestrians in an image, for example, I will define a huge family of possible solutions. Okay, that's called a hypothesis space. Okay, that's a predefined set of possible solutions. I'll give examples as we go along. For now, you could just think of this abstractly. And in addition to this hypothesis space, I collect training examples. I collect examples of an input to my system and the output that I would like it to produce. Okay, so for example, if I want to have a program that tells me what an image contains, I will collect a lot of examples of images with different objects, and I will have their labels, what I would like my algorithm to produce for these specific examples. Okay? So instead of just handcrafting a single solution, I define a big family of solutions, and I collect training data. And then basically the approach is as follows. I feed these two entities into what is called a training engine. And this engine chooses the algorithm. It chooses the solution inside this family that best agrees with the training data. Okay? It chooses a solution that will comply with these examples, that will explain to you the examples that you gave it. Okay? And then you take that final chosen solution, chosen algorithm, and you go ahead and apply it in the world. That's the basic idea behind statistical machine learning in its basic form. Instead of explicitly designing a solution, I define a big family of solutions, I collect examples, and then I choose the specific solution that best agrees with the examples and go ahead and use it. Okay? So if you sweep away a lot of the details, this is the flow, and it's very simple, but yet it's something that is quite unorthodox and original. Okay? We're solving something that is incomprehensible for us. Okay? We don't know how we see. We don't know what are the rules that are governing our brain when we detect objects. Okay? And so instead of trying to do this, we just collect a lot of examples, define a family, and choose the one that agrees with it. Right? So statistical machine learning has a lot of applications. Okay? You encounter it all the time. Okay? Google, Facebook, even cars, everything that identifies the content of images or is able to translate text or understand speech, right? Or give you recommendations, it's all based on machine learning. It's all around us. Right? And the basic design flow, if I have some problem and I want to solve it with statistical machine learning, then there are two basic steps that I need to follow. Okay? First of all, I need to choose that family of algorithms, that family of solutions, that hypothesis space. Right? And there are different types of families, and they have different names. Okay? So, for example, decision trees, that corresponds to a certain set, a certain type of families. Support vector machines, that's something else, and deep neural networks, aka deep learning, is a different type of family. Right? After defining and choosing my hypothesis space, I have to design my training engine. I have to define how I am making that choice, how I'm taking that specific member of the family that fits the training data, how do I find it, and what's the criteria for choosing it. Okay, and there are different technical aspects here. Some of them were written down here. At the end of the day, you need to define some sort of an objective and then some algorithm that minimizes this objective. Okay, you frame the search as minimization of some big function. You need to decide how that function looks like and what algorithm you use to minimize it. Right? So that was statistical machine learning in a nutshell. Okay, crash course on statistical machine learning. And now let's go ahead and talk about deep learning. Okay, so I assume in the media, a lot of what you hear about deep learning is in the context of artificial intelligence and works like the brain and things like that. The definition that you will see here is very, very different and maybe a little disappointing. Okay? But that's how I view deep learning. Okay, so at the end of the day, the definition of deep learning in its broadest form is as follows. My hypothesis space, okay, that family of solutions, that family of algorithms that I'm defining is compositional. Let's explain what that means through an example. Okay, suppose I want some algorithm that takes an image and returns some label that tells me what the image contains. Right? So in deep learning, the kind of transformations, the kind of classifiers that I will work with, the families that I will work with, have a structure of the following type. The input goes through some transformation, okay? And then there's this representation. Then it goes through another transformation, and then there's this representation, and then there's a transformation that produces the output. So in this case, the input, an image, is mapped to the output, a label, through 3 transformations. Okay? Each one of these transformations is called a layer, and every transformation has parameters that you can tweak, and it would change that transformation. Okay? So the transformations themselves are called layers, and their parameters are called weights. I'll give a specific example in the next slide. Are there any questions about this? Okay, I'll give a concrete example. For now, what you see here is just that inputs are mapped to outputs by composing transformations one on top of the other. That is what deep learning means. Okay? It means that you're working with a family of transformations that is compositional. Okay? All right, so let's give a concrete example. Okay, so this is the most basic, I guess, fundamental deep learning architecture. All right, suppose I would like to map my input, could be an image, for example, to some output, which could be a label or a number. Okay, like the probability that this image contains a dog. It's just a scalar, single number. Then this type of architecture, this type of family of functions, which is called, it's an explosive name, feed-forward fully connected neural network, operates as follows. I take my input, that's a vector, I multiply it by a matrix, and then I pass it through some function that takes each element and applies some nonlinearity to it. Then again, I multiply by a matrix, apply a pointwise nonlinear function, do it again and again and again. Every matrix multiplication followed by pointwise nonlinearity is called a layer. Okay? So this kind of architecture can represent a lot of different mappings. And I obtain these mappings by tweaking these matrices. They are called weights. So if I vary these matrices across all possibilities, then I get all possible mappings, all possible solutions in this family. Okay? So basically, that is what deep learning is. Right? So there's a reason why I guess a lot of you are here. This is something that is really, really successful. Okay? It really transformed the face of technology and also, I guess, our lives as consumers. Up until a few years ago, applications such as image recognition or speech recognition or translation, you probably remember, they did not work that well. And there was a big leap in performance, and it's all thanks to deep learning. Okay? Your phone right now includes dozens of these deep learning architectures, dozens of neural networks performing different tasks. I guess some of them are listening to me right now and sending it somewhere. Everything you use that involves detecting the content of images in Facebook or other things, or when you use a system that identifies your voice or understands your voice, like when you speak to your phone, or when you translate with Google Translate, it's all based on deep learning. Okay? So those of you that have, I guess, been around for a while and are interested in neural networks know that they're not new. Okay, the same type of algorithms, these compositional functions that I just described, they were invented at least maybe 70 years ago. 80 years ago. And there's a question of what's new. Hey, why does this work so well now? What happened? And the answer, which is somewhat disappointing, is that it's mostly about the strength of computing systems. Okay, we now have the ability to perform much more computations than we did in the past. We can collect a lot more examples. The internet is much faster. We can download much more images. We can store a lot of images, for example. And we can store large data sets. And so we're just training much, much larger models with much, much more data. And that's what makes it work so well. Okay? It's almost entirely about that. The algorithmic improvements, either in the way that the network architecture is structured or in the algorithm that you use for training, there are some innovations here, but it's relatively minor. It's mostly about the computing power. Okay? So this is the part where I should be extra careful. Let's just say that in my view, sometimes deep learning is misrepresented, okay, or portrayed in a way that goes way beyond what it is in practice. Okay, so, for example, I suppose you hear a lot that deep learning works like the brain. So, at least in my view, it's inspired maybe by the brain, but we have no idea how the brain really works. Right? It's a human, I guess, habit to take the newest technology that we don't understand and say that that's the brain. Okay, the brain used to be a graphical model, and now it's deep learning. A lot of different things are kind of arising. A lot of companies, some say that they apply brain-like intelligence to analyze financial markets, things like that. And one of the objectives, or maybe the objective of this talk, is to kind of try and give you a more scientific view of what it means, okay, and what we can do and what we can't. Okay, so when you go ahead and apply deep learning, then you have to do two things, what we talked about. You need to define that family, that network architecture, and you need to decide how you train it. Okay? So typical questions that one faces when you want to implement a deep neural network, okay, and you need to define its architecture, what kind of transformations there are, and different sizes of different layers, things like that. You need to come up with a concrete architecture, just like the one that I showed with matrix multiplication followed by nonlinearity and so forth. That's a very special case. There are millions of other possibilities, and you need to choose specifically what you're going to use. Right? Next thing you need to do is define how you train this thing. Okay? What is your objective function and what algorithm you use to minimize that objective function, how you find the weights that will agree with your training examples. Okay? So at the end of the day, these are the two things that one needs to do. And I'll just try and kind of portray the state of affairs right now. okay, and how people apply deep learning. So in terms of choosing your network architecture, the fact of the matter is that right now there are a few standard templates, okay, that people have designed over years and decades of research. Nadav Cohen gave her a talk last year, I believe. He's one of the people that is responsible for designing these templates, specifically ones for images, okay? Also things for speech and text. And most of the time, almost all applications these days of deep learning typically just take one of these templates and tune them based on trial and error and based on conventional wisdom without a real profound understanding of what it means to tweak your network architecture. Okay, we just take something off the shelf, tweak it, tune it a little bit based on what our friends told us, and we try out some things, choose what worked best, and that's it. And there's really no principled way right now to choose your network architecture. The templates that people developed, they might not be the best thing that one can come up with. Okay, they worked really hard to get there and to design these templates, but maybe they're not the best thing. And even worse, if you try to apply deep learning to new types of problems, then it's pretty difficult to come up with a reasonable network architecture, okay, to define a reasonable family. Usually what people do is just they adopt one of these templates and try and kind of force them to do what they want. And I would kind of give this analogy where we have this square template, we want to fit it into this round hole, and we just tune it and carve the edges until it fits. But right now, we don't know how to design these round cylinders. Okay? We have these boxes that people designed over decades, and because we don't really understand what's going on, we just look at what we have and try and make the least changes possible so that it would fit. Right? In terms of defining how you fit your training data, okay, the training procedure, the situation is, I guess, somewhat similar. So here, the way that things are set up, without getting into too many details, is adopted from classical machine learning. Okay, the way that things are set up in classical machine learning, which are other types of models that are simpler, there are explained ways on how you should set up the training, the training engine. And for deep learning, we just adopt it as is. And there's a gold standard algorithm. It's called stochastic gradient descent. Maybe you've heard about it. Deep learning is entirely based on stochastic gradient descent. Okay? Everyone uses this. And again, this is something that's adopted from classical machine learning, and we don't know, there's no reason a priori for this to fit deep learning. But in practice, it does. And we don't understand why. It works miraculously. Okay? This training procedure somehow succeeds with SGD, stochastic gradient descent, and we don't really know why. We just know that there are a set of standard practices, and if you follow them, it's going to work. Okay? That's what we know, and this set of standard practices was reached over decades of research. Right? But that does not mean that that is the optimal set of practices. And also, it was designed for mainly with applications for image, speech, and text analysis in mind, and it's not necessarily the best thing to do for other applications. Okay, so here too, we're shaving the sides of some box to fit in a round circle. Okay, so there's a question of, did deep learning solve artificial intelligence? So here are two competing perspectives. You can understand by the pictures which one I belong to, which school I belong to. Okay, so some would say that, yes, it works just like the brain, and it can learn to do whatever we can, and experts know why it works and how to operate it. So this may be a little extreme, but I think the the way that this technology is portrayed in the media is not so far from this perspective, oftentimes. Most people that kind of address these problems and think about this technology from a scientific perspective would say that no, it's an effective machine learning model, and it's very successful empirically. We see that it works very, very well for very specific problems, and no one really knows why it works. It's operated based on decades of trial and error, essentially. And it's kind of perspective that I'm trying to convey here and in general is that to take deep learning to the next level and to really get closer to the capabilities of human intelligence, we need to develop theoretical foundations and understand what's going on here. Again, one of the main purposes of the theoretical machine learning program here is this: to try and develop a theory behind this technology. Okay? And ultimately, most of us are driven by the belief that it will work much, much better, and it will be safer and more robust once we understand it. Okay? So, is there light at the end of the tunnel? I'm not sure. But a lot of people are working on this, a lot of smart people, and progress is being made. And I will give you just a taste of the kind of questions that people ask and the kind of answers that people have. That may give flavor of what's going on these days. Okay, so one line of question that people are working on, one line of questions that I've worked on personally as well, is to try and characterize what are these transformations that a deep network can realize, and how do these transformations depend on that architecture, how many layers you have, and things like that. Okay, the fact that these simple transformations, these compositions of transformations that reside on your phone can classify images and understand images is highly non-trivial. They can somehow represent functions that do very, very interesting things. And it's a priori completely not obvious. Okay? So the kind of things that people know are, for example, we know that if you have a lot of layers, if your network is deep, then you can represent classifiers and mappings that if you try to represent the same things without having a lot of layers, it's not going to be feasible. Okay, you're going to need an exponential number of computational resources. Okay? We also know for different types of architectures, very popular ones like CNN, which means convolutional neural network, we know that there's certain aspects of the way these networks are structured, and we know how these aspects affect the ability of a network to model correlations between pixels, for example. Okay, so if I want my deep neural network to perform some medical imaging task and tell me if the image, the blob in the image is symmetric or not, then that network needs to model correlation between pixels on opposite sides of the image. Okay, but on the other hand, if I'm just classifying cats or dogs, then maybe I only care about correlations of pixels that are nearby. And we know how you should tune your architecture to support one task versus the other. Okay, so that's kind of an initial example of how theoretical understanding gives rise to concrete guidelines on what you should do to solve a problem with deep learning. Okay? Another line of questions is the following. That is, okay, so I take my deep neural network and I fit it to training examples. Why should that network that I trained, or that specific transformation that I chose based on training examples, why should that do a good job on images that it has not seen? Okay, and if I have a model with billions of parameters and I train it using tens of thousands of examples, then from statistics we would assume that this model that has so many parameters compared to the number of examples that you showed it will not do a good job on images that it hasn't seen. Okay, there's a notion called overfitting. And it doesn't happen with deep networks, and we don't really understand why. Okay? There are recent works, some of them were done here, last year, for example, to try and characterize what it is about these networks that make them not overfit. Okay, what it is about them that makes it possible to tune a billion parameters with tens of thousands of examples, and then it would still work well in the real world. Okay. Another line of questions is this search procedure that we just follow standard practices for, why does it work? Okay, we know in theory that it's not necessarily going to work. Okay, we know in theory that there are cases where it fails. Okay? And usually in the theoretical computer science, maybe not usually, but a lot of the times, people are interested in analyzing the worst possible case. And people have done this for deep learning, analyzed what happens in the worst possible case. And we actually know for a fact that nothing works in the worst possible case. Okay, so in some sense, deep learning provably fails and yet works in practice. The reason is because what happens in practice is not the worst possible case. Okay, there are some typicalities that characterize reality. And we're having a difficult time adopting this mindset and making assumptions and modeling what happens in the real world. And this comes across, for example, in the question of how you can train a network with SGD, because in the worst case, we know you can't. Okay, so there are different types of results here too. I personally had to work here in this group with Sanjeev. These days, we know for very simple types of models, we know that there's something very special about deep networks that makes SGD work. Okay, but we know it for very, very simple models. We don't know it in general. We don't know it for the interesting models that people use in practice. Okay? So I guess I'll now conclude. So statistical machine learning is a rather radical approach for solving problems. Okay, instead of taking a problem that I know something about and designing a solution, I just predetermine a big family of possible solutions, and I collect a lot of examples of what I want my solution to do, and then I choose based on that. It has enabled us, mankind, to solve a lot of problems that we weren't even close to solving before. Deep learning, that's a special case. And what characterizes deep learning is that these families of solutions, these hypothesis spaces, are compositional. You compose mappings one on top of the other. And it's very, very, very effective on specific tasks. Okay? Other statistical machine learning models have enabled us to reach a certain level of performance in image recognition and speech recognition and text analysis. And deep learning, that was a huge step forward, the use of deep learning for these problems. That's a special case. Nonetheless, at least I believe that this is overhyped in general. And it's being presented as something that will bring world peace one day. But it has a lot of limitations, and we don't know much more than we do know. It works on very, very specific tasks, and I encourage you all to take what you read, sometimes in kind of popular media outlets, and what you watch in films, take that with a grain of salt, okay? Because we really have very little clue of what's going on. This is basically a science that's driven by decades of trial and error. Okay? And I believe that to take it to the next level, we need to develop a theoretical understanding behind that. And that's kind of what I've been doing for the last several years, and that's what I'm doing here. And that's one of the main purposes of the group here for theoretical machine learning. And I think that this is becoming one of the strongest centers for these type of questions in the world, basically. And next year there will be a special year devoted primarily to this topic. And I'm really excited to be a part of this. And I thank you all for supporting this program and the IIS in general. And hopefully in a few years, we will understand what's going on. Well, thanks.